Well, thank you. Thanks to the organizers, Damien and Rick and Chris. I really enjoyed this talk, and thanks to you collectively, both for good talks, but also for some interesting conversations. And yes, I'm talking about photo effects, but these are on a macro scale compared to what you've heard so far. Our devices are relatively large area, so we're dealing with billions of molecules. They're oligomers, were grown via radical reaction, so they're covalent throughout the entire structure. And I say nearly here because we're not sure about this interface. We are sure about this one being covalent. And the difference between these two will become apparent in a little while. And we've been making these things for a long time. And here's a cross-section TEM of a bromo derivative. And the bromo film is about 5 nanometers thick. And the interfaces aren't perfect, but they certainly are. You can make them in high yield and very reproducible in a lot of different forms. We made these early. This is 1,800 molecular junctions on a 6-inch wafer. These end up getting packaged in this thing. And actually, we sell these things. There's about 1,000 of these out in the world of electronic music. And they're molecular junctions. They're based on azobenzene, not on fluorine, but it's still a tunnel junction. And of course, our whole motive here and the sort of context for this talk is the question that many of you have been looking at. How do molecules behave as circuit elements? How do they conduct charge? What can you do to control that? And secondly, what can you do with it that you can't do with silicon? I mean, I'm not talking about Moore's Law. I'm not talking about replacing silicon. I'm not Don Quixote and the windmill, right? I think silicon does a great job, but there are things you can't do with it. And this commercialization is an example of that. Okay, so is the electronics molecular? And this is a question that's under a lot of your work, collectively our work, is how does structure affect performance? And you want to see some significant effects of structure on transport. And in this case, we're talking about 8 nanometer devices. So it's an oligomer, it's 8 nanometers long, about 10 molecules. And you can see the different structures. And clearly, there's a very large difference in behavior, 6 orders of magnitude, even though the thickness is 8 nanometers and the bias is 0.5 volts. So the big question to us was why is that? And I'm not really going to answer that today. It's another talk, but I do want to show you about how photons can tell you something about this story. So let's look at the way that photo effects that have been observed in molecular junction. We're just considering kind of a simple diagram, cartoon. And there have been several examples of this. Internal photo emission was a technique that actually was discovered in the late 70s, and there was a book about it in 2008. Internal photo emission, unlike Einstein's photoelectric effect, you don't eject the electron into a vacuum, but you eject it to the point where it can cross an orbital, and in this case a LUMO. And we exploited this to look at barrier heights and such things. And it's useful, but it's not. I'm going to talk today mostly about optical gap transitions, where you do this excitation, and then the question is, what happens next, and how does that behave? And there's been some passed on that, some theory from Nitzan and Galperin and Carlos Cuevas, and then after experiments that we've published quite recently, and I'll talk about these in some detail. There are, of course, other things that can happen. You can have hot electron and plasmon emission, which is the macro version of the STM you just heard about. This one is one example of STM used to generate light. In our case, we published this with a postdoc named Ivashenko. And in this case, the electron is ballistically transmitted across the junction, becomes a hot electron. That hot electron can emit light. And under the right conditions, the wavelength, the maximum energy of this light is equal to EV, the voltage of the bias. And that's quite interesting. You can look at energy loss, for example, in that story, and that's what these papers are about. And then another one is a bipolar injection model, which is done in ruthenium bipyridine. And here you inject an electron on one side and a hole on the other side. They propagate to the center and emit light. And this was done on a thick film scale 20 years ago by Alberta, among others. We're doing it on something that's more like 5 nanometers or 10 nanometers thick, and that emits light. And it's actually a fairly efficient OLED, although that wasn't our motive in doing it. Okay, so let's consider this case, photo effects where you shine light on the sample and generate current. And the experiment is not complex. Actually, this was based on the 2015 work that Jerry Ferriero, who you heard from with David Kahn's talk, he developed this initially. So we have our junction, and we shine light on it, either from a xenon arc or from a laser, and then we measure the photocurrent. It's simple. It's usually chopped. Usually we're using a lock-in to detect it. And you get something that looks like this. Photocurrent's at zero bias, right? So effectively, the junction is short-circuited. And you get a photocurrent. And this is the light intensity. And of course, you have to take these two together and calculate some sort of yield. So this is the yield as electrons per photon. You can see it's not very good, 10 to the minus 6, 10 to the minus 5. But you get that from the correction for the output function of the xenon arc. Then you also get a phase, and the phase tells you about the polarity of this photocurrent. We'll have quite a bit to say about that. Okay, so this is the external quantum efficiency, and you can see they're nanoamp type currents typically, or even picoamps, but measurable. And then the phase indicates the direction. So let me show you one example initially, and then we'll look at quite a few in a minute. This is a fluorine molecule. There's a NH2 here that we use to bind it to the surface, but this is fluorine in acetonitrile. And it's got the usual UV-Vis spectrum. Now you bond it covalently via diazonium reduction, this radical-driven process, so that it's now bonded to the surface, and you have an oligomer of roughly 5 subunits. And these aren't assembled like a SAM. They're somewhat disordered. But the good news is they're very strongly held. This is a very strong bond, both between the molecule and the surface and between the molecules. So they're very stable. That's why we can sell them to people and they don't go bad after a few minutes. Anyway, you look at the absorption spectrum of the molecule on the surface, and you see there's quite a bit of broadening here. And that's telling you, one of the things it's telling you is there is a fairly significant electronic interaction between the carbon and the molecule. However, you can do this a little more extensively and go through the entire device. And the entire device can be made about 20% transparent, which is enough to do spectroscopy. And you do that, and you measure the absorbance, and then subtract out a blank from the blank junction. And you get this curve. Okay, so it's telling you that yes, it absorbs light. It's a thin film, a couple of nanometers thick. But it absorbs light, and that light is somewhat broader than it would be in the UV-Vis. But the question for us, of course, is what is the consequence of that reaction, or that process? And here's the photocurrent yield that you get if you measure it and just put it on the same, or normalize them so they have the same height. And you see that the photocurrent yield more or less tracks the absorption spectrum. So we looked at that in a little more detail. That's what you just saw. This is another molecule, diimide, naphthalene diimide, quite a clear correspondence between the photocurrent and the absorption. This is anthraquinone, where it's not as clear, and then this is nitroazobenzene, where in several examples, and there are actually 8 different examples that I'll show you in tabular form in a few minutes, 8 different examples, it pretty much tracks the absorption spectrum, except for these rather deep UV absorbers when the band gap is fairly large. There, the agreement is not as good. but it's still qualitatively very similar. Okay, well, you can also look at sine. And sine's a little tricky. You have to be very careful how you define your terminals. I'm just going to give you the results here. But this is what I'm calling a positive photocurrent. And the way you tell that it's positive or negative is by looking at the spectrum. This is the photocurrent yield versus wavelength. And so I put 6 different molecules here. Obviously, some of them are negative and some of them are positive. And that's an important clue as to what type of carriers are involved. You also can look at photovoltage. Just have it at open circuit into a high impedance voltmeter. And you can watch the photovoltage develop as a consequence of the light. And it looks something like this. You get, in this case, a positive photovoltage whenever the light's on. That's for the case of fluorine, which is this one. And then you look at NAB, this one, and it's the other direction. So the photovoltage is giving you a clue as to the nature of the carriers that I'll tell you about shortly. Okay, another thing we can do is simply can make both sides transparent, at least partially transparent. We can illuminate it from either side. And that's an important test because it tells you that it doesn't matter whether the light comes in from the bottom or the top. You get pretty much the same spectrum, certainly the same sign. The only differences here are due to the fact that one of these films is a little bit thicker than the other. That's what gives you the different height. And this feature is actually related to the source. Okay, and also the photovoltage is independent of which side you shine the light on. Okay, so what have we learned from this? Oh, let me summarize the whole work. These are 8 different molecules, and these are the DFT predicted free molecule energies for the HOMOs down here and the LUMOs up here. And obviously, we're looking for some kind of a relationship between the photocurrent, both sign and magnitude, and these orbitals. And if you look at the data I just showed you, you see that these molecules have a positive photocurrent and a positive OCP. And that's a pretty simple measurement. And notice that in these molecules, it's the HOMO that's closer to the Fermi level than the LUMOs, which are up here. Okay, if you go to the other side, this is molecules with a negative photocurrent and a negative OCP, and they're the electron acceptors, nitrophenyl and anthraquinone, et cetera. And here's the Fermi level of the carbon that we're using, which is measured with Kelvin probe and UPS. Okay, so there is a correlation. And that was fairly intriguing because it said that if you know the sign of the photocurrent or the sign of the photovoltage, then you can tell something about which orbital is closer to the Fermi level. In other words, whether it's hole-dominated or electron-dominated. Okay, so just to summarize a few points here, polarity depends on the molecule. Polarity and OCP are consistent across 8 different structures. PC spectrum tracks the molecular absorption spectrum, independent of illumination direction, and so-called donors, meaning things that have relatively high energy HOMOs, yield positive photocurrent, whereas acceptors, which have relatively low LUMOs, give you negative photocurrent. So those are the facts. Now, why is there a photocurrent at all? Because this is more or less symmetric device, almost symmetric device, and almost is important. Because we're pretty sure, we are sure this is a covalent bond. We're not sure this one is. So there needs to be some asymmetry here if you're going to have a photocurrent at all. Otherwise, it just should be 0. The electrons and holes should go both directions. Well, fortunately, Galperin and Nitzan did some theory quite a while ago about this and said that you can get that asymmetry if the coupling is different between the two electrodes. And this is this is a fairly complex story, and it's here. Well, I'll give you the summary of it. Let's consider so-called donor molecules that have a HOMO closer to the Fermi level. And just separated molecules. So here's the Fermi energy. Here, I'm just writing in 8 molecules here just to indicate the oligomer. And that's the energy scale. But of course, this is when they're isolated. And everybody knows, and we've already heard from a few people today, that when you put the thing together, things change. So if you look at the actual device, you get electronic coupling between the donor and the contacts. And you generate a potential profile with built-in field inside the device, which is related to the coupling. And the stronger the coupling, the more the shift in this local potential. And this is the vacuum level alignment, or lack of it, dipole effect, whatever you want to call it. It develops an internal field which has a direction as shown. So if you put light in, you generate a carrier. That carrier, in this case the electron, is going to go down this potential profile. And that's what gives you the asymmetry. So the donors will do this because the donors have a little bit of charge transfer from the molecule into the contacts. And so that gives you a positive photocurrent. And this happens, at least you can draw the diagram for these molecules, anthracene, fluorine, et cetera. These are all so-called donors. Well, if it's an acceptor, it goes the other way. So an acceptor gets bent with downward on this side because electrons have come from the contacts into the molecule, partial charge transfer. And so the sign of the photocurrent indicates whether the HOMO or the LUMO is closer, because whether the HOMO or the LUMO is closer determines the internal field that is driving this photocurrent. And as I say, there's a lot more about this here, and Nitzan and Galperin predicted all this in 2005. Okay, well this works for zero bias. But let's suppose that we apply a bias, and we were very interested in this because we figured that if you have a dark system, you're considering just the system at rest without any excited electrons. But if you have light shining on it, now you have a carrier in the LUMO and HOMO. And so how do those behave in terms of their IV behavior? So Amin Morteza did this work, a very talented student. And let's see what happens when you have a bias of 0.2 volts. Small bias, and this is dark current, and you have a little bit of dark current because you get a little bit of current that you saw earlier. You turn the light on, you get some total current. Turn the light off, and you can talk about this difference here being the photocurrent. And this is interesting. In fact, you get about 75 nanoamps in this case. If you did it with V equals 0 for the same device, you get 0.2 nanoamps. So clearly the photocurrent is a lot larger than the photocurrent, a lot larger than if it were when it's under bias than when it's at V equals 0. And you can do this once, you can do it lots of times. Here's about 20 or 30 of them. Just go back and forth, turning the light on and off. It's a very robust phenomenon. All you're doing is moving electrons around. You're not changing structure or anything. Okay, so you look at the IV curve in the dark. It has the shape of some of the ones you saw earlier. Fine, you turn the light on and you get a lot more current. And if you plot them on a log scale, you find that you get a factor of about 1,000 at 0.1 volt increase in current due to the photo effect. And the power here is quite low. This happens to be with a laser, but it's less than a milliwatt on a square centimeter. Okay, dark current. Many of you have studied this a lot as a function of thickness. We did too. This is what it looks like from 3 nanometers to 8.6 nanometers. And there are several papers that I won't talk about. We discussed the possible mechanism for that. But what I'm going to emphasize here is what happens in the photo effect. So you take this curve up here and say, here's a 407 diode laser. That's that point. Now look, change thickness, and you get a very different picture. They're almost thickness independent down at low bias, and very different shape. Obviously, very different factors are controlling this photocurrent than were active in the dark. Okay, so let's do a beta plot. Log J at V equal 0.1 volt versus thickness. And you get this for the dark, beta of about 2.1, which is typical for aromatic molecular junction. Been reported by many people, which corresponds to a factor of about 8 per nanometer of attenuation. The light current, however, is almost thickness independent at low voltage. And 10 to the 4th increase, and we've seen this as high as 10 to the 5th for certain systems. So it's clearly a very different animal. And instead of having attenuation of 8 per nanometer, it's now only 14% per nanometer, beta of 0.13. And about this time in other work in the lab, we were wondering if this picture looked a little different if you did it at constant field instead of constant voltage. Usually we do it at constant voltage. But let's look at a constant field, 0.5 megavolts per centimeter, which is about half a volt on the actual junction. Now you get a rather interesting picture. Here's the dark current, and here's the beta plot, same one as that. This is when you look at the photocurrent. So this is actually the difference between dark and light. That's what this is. And this is the optical power. And notice that we start out at low power. You have a beta that's small, plotted versus constant field. And as power goes up, the whole thing goes up. And of course, what you're just doing is you're elevating the photon current above the dark current when you do that. And the beta is essentially zero statistically zero at constant field. So it's pretty small up here, but it's even smaller if you plot it at constant field. Okay, well, obviously there's a lot to this story, and let me show you a little bit more. This is what it looks like when you take a absorbance of 8.6 nanometer device in a complete junction. And that's after we've subtracted off the electrodes. That's the real absorption of the molecules inside the junction. And you plot that along with the photocurrent and find that they're very, very similar. And we've only done this in detail for a couple of molecules, but I'll just remind you of what I showed you earlier, that at zero bias you also get a correspondence between the photocurrent and the absorption. This is another one, porphyrin. Porphyrin's nice because it has lots of structure in it. And so you have structure not only in absorbance, but also in the photocurrent. Pretty good signature. That's really what's driving the thing. And you can do these spectra as a function of bias between plus or minus 0.3 volts. You get the same spectrum. We haven't gone farther than that yet. We did a whole bunch of voltages between those two, and they're not voltage dependent. Magnitudes are, yes, but not their shape. Okay, temperature. Temperature, of course, is particularly interesting here. If you're talking about transport, temperature is huge. So the temperature dependence for nitride is benzene at 0.2 volts. The dark current, notice I haven't plotted this Arrhenius style. I'm just giving you the raw data here. This is what the dark current looks like. And if you do turn it into Arrhenius type plots, it's not a very pretty Arrhenius plot. It's curvy. But anyway, you can look at the local slope, and you find that at low temperature, the slope is really quite low on an Arrhenius plot. At high temperature, it's a bit larger. And I'll show you more of that in a minute. If you do the light, it's flat. And this was a little bit confusing to me, because I said, well, this is total current. This is light plus dark. And it's just plain flat. And if you subtract dark from light to get just the photocurrent, so we're plotting just the dependence of the photocurrent on temperature, you find that it has an inverse Arrhenius dependence. So clearly, this and this have very different temperature dependence. One explanation is the same one you use for metals, and that is that you have less scattering at lower temperature. Therefore, the conductance goes up at low temperature, and that's what we're seeing. That's one possibility. I wouldn't say yet that that's the case. Notice the PC is decreasing, photocurrent is decreasing by 30% between 80 and 450 K. Inverse Arrhenius dependence. And Michael Galperin took this on and did some theory, which was just published recently, and he was able to reproduce this qualitatively, at least, using a combination of Hubbard and Green's function techniques. And I would say that he can make it fit, yes. I wouldn't say that doesn't necessarily mean we understand the whole story. Okay, so how about beta? If you look a little bit more at beta and some other molecules, this is work that's relatively recently published, but it's in different molecules where you see huge differences in the beta plot, log J versus D for different molecules. Okay, you see it's very interesting. It's an entire another story, but you see this steep part, which is about 2 to 2.5 per nanometer. And everything does that at low thickness, everything we've studied anyway. Alkanes are down here, and they're even steeper with a slope of about 8.6 per nanometer. Now, some aromatics just keep going. Anthraquinone is one, and so is fluorine. Others, like NAB, the molecule we've been talking about, bends over, and a lot of them do this. And we have this paper is all about that, and we're working more and adding more molecules. What I want to point out here is that our NAB data, oh, right, and the beta, you get to 2.1, you saw earlier, and then this is 0.18 at high thickness. Now, this is dark, right? No photo effects yet. Okay, we did the temperature dependence you just saw, 7.4 nanometers, and that was it. Time to write the paper after we did that. So let's look at some other cases. What happens if it gets thick? Now, I think that most of anybody in this room would agree that 33 nanometers is too thick for coherent tunneling, right? So what goes on with both the dark and the photocurrent when it gets to be thick? And so that's what's next. Right, so here's thick NAB, 33 nanometers. And yeah, there's a temperature dependence in the dark. It's not terribly different from what you saw earlier, and I'll give you the numbers in a minute. If you turn the light on, very different behavior. You get current at low bias immediately. Of course, it's easy to get current at low bias because you're putting the electrons into the orbitals that carry it. You're generating carriers from the light, as opposed to down here where you're having to generate carriers by injection. If you do the Arrhenius format for 1.5 volts here, this is what you get for the dark. It's got about 100 MeV and 3 MeV. If you do it with light on, you get the red curve. If you subtract off the dark current, you get this curve almost the same. And the slopes are 21 and 0.7 MeV. Now, notice something very interesting here. Even though this current is way lower than this current, the slopes are close to zero. So we're having an activationless process, whether it's the electron up in the LUMO that we've generated from photons, or whether it's something else in the case of the dark signal. And I'll tell you what I think that something else is in a minute. Okay, so I'll call these interim conclusions, and we can certainly argue about them if you like. First of all, the similarity of absorption and photocurrent spectra indicates optical excitation across the HOMO-LUMO gap. I had this conversation roughly a year ago with Carlos Cuevas, and he said, that sounds like a band gap spectroscopy. Oh, really? Okay. All right. Secondly, once the carriers are in the molecular layer, there's minimal attenuation. Now, yesterday we heard David talk about in and out theory. You have to get the carriers in, which is hard to do at low bias. Injection is difficult. That's why the current is so much lower in the dark. But once you get the carriers in there, there's minimal attenuation. So this implies that transport is close to resonant between lumos. And at constant field, it's not attenuated. So LUMO-LUMO transport barrier must be lower and shorter than this barrier. Okay, so what about temperature dependence? And we see a region where we thought Schottky injection, and there's a couple of papers one by Florian Rokem about the Schottky equation on the injection part. And just to remind you what this looks like, this is from Say's book, Bible of Semiconductor Physics. And if you have a barrier and you apply an electric field to that barrier, the barrier gets lowered by a simple equation. It says that the new barrier is lower by this term of Q over et cetera times the square root. That should be the square root of the electric field. What we think is happening is that in this region, you're actually going over this now slightly attenuated barrier. And that's where you're seeing the temperature dependence. And you get out to here, and you say, well, gee, this can't be thermal. It's too weak over a wide temperature range. So we think that that's tunneling through this injection barrier. And this is sometimes called the injection problem of semiconductor physics. If you have a Schottky contact, you have this barrier, you have to get through it somehow. You can either do it by direct tunneling, as shown here, or something that some people call thermally assisted tunneling, where you have a little bit of excitation in the contact, which is thermal, followed by a transfer to a shorter barrier. And if this is all true, then the plot of, then the current should be proportional, the log of the current should be proportional to e to the 1/2. So I did that plot, and predicting that log j, which is proportional to the barrier height, should be proportional to e to the 1/2. And sure enough, it is. And not only is it very straight, but also you have a different slope, a very different slope for the dark than you do for the light. So I call this a plot in progress, and it's okay, it's the last one. A plot in progress, because this is data from the past. I just started to put this together with older data and newer data. This is the NAB dark that you saw earlier that was done in 2018. This is the NAB light that was done in 2019, except now it's at 0.5 volts instead of 0.1 volts. And then just last week, we got a couple of more points to add to this. This is NAB in the light and thicker. So our 33 nanometer junction is up here, and one at 15 here, and another point down here. So you can see that the NAB dark is reproducing as it should, what we did a year and a half ago. But with this light, you're still getting a lot of gain. And this gain is, in this case, is a factor of 170. Now, in other systems that I haven't talked about, we get that can be a 10 to the 5th. So we can get a very high photometric gain. And so we think that this is our working hypothesis. That this is injection limited. And here you got to blast across the Schottky barrier to get the electron into the carrier, into the layer, whether it's a hole or an electron. And many molecules look the same in that region, many more than I've shown you so far. Activation of roughly 100 MeV, exponential with distance. I'm not going to call it Schottky, but I think Colin Van Dyke, who's working on this as well, and some of you know him, is doing some of the theory on this, and it's a modification of Schottky. It is a field-dependent barrier, right? Whereas here, you're in a region where it's bulk limited. so it doesn't matter how thick it is. This is at V equal 0.5. Remember, if we plotted a constant field, this would be horizontal. And here you're talking about electrons that are, carriers that are already in the system. You put them in from the photons. They move easily. So as David's called it, the in and out hypothesis, you got to get the electrons in. Once they're in, they go quite easily. And so here you're talking about electrode to LUMO transport, the injection barrier that's so familiar to the semiconductor world. Here you're talking about LUMO to LUMO transfer, which to a chemist anyway is a lot more interesting. And we're able to track that. So what we're doing with the photocurrents is really looking at the characteristics of this type of transport rather than this type. People, did a lot of this work. These are all postdocs. They all helped. He's now at the University of Toronto. Colin van Dijk just started at the University of Mainz in Belgium. Very good theorist. He spent some time with Mark Ratner, and he's responsible for a lot of what I said about Schottky effects. So I think we're going to use this both as a diagnostic test for the identity of the carrier, but also as a probe of longer range transport with these easily generated carriers. So thank you for your attention.